Hello, and welcome to a shallow dive on continuum mechanics. You can find a bunch of super smart people defining continuum mechanics by Googling it, Binging it, or, if you've decided to never be able to run engineering programs on your computer, you could use Safari on your Mac. But if that's too much effort, let's get into it. Continuum mechanics is, basically, the term used to clump the other mechanics you'll learn as an undergrad of mechanical engineering together. It consists of solid mechanics, fluid mechanics, and heat transfer/thermal mechanics. Well, that's not so bad. Sounds easy enough, so what's the longer answer? Mechanics is pretty generally understood to mean, in layman's terms, that it's the math behind motion and forces, or, in layman's terms, in even more simple terms, stuff happening to stuff. Continuum basically means continuous, and in this context can be described as over a period of time. The length of that time can be broken down into finite and infinite, and the importance of the distinction is easily shown by the difference between thermodynamics and heat transfer. I think it would be best to quickly go over heat transfer, as it's super intuitive to understand the core concepts of the subject, while the more in-depth aspects are harder to grasp, as shown by thousands of students' transcripts. If you don't know what heat is, it's the thing that made my hand hurt when I was 12 and touched the heating element of my toaster. And transfer is what happens when one thing goes to another thing, like my tears transferring from my face to my paper while studying for heat transfer exams. So, heat transfer is energy going from one thing to another, and a good example is heating up a pan on the stove to cook Hot Pockets the right way. So, assuming the stovetop burner has the heat evenly distributed, and the bottom of the pan is entirely within the burner, the question that heat transfer answers is, what temperature is the pan after 10 minutes? Thermodynamics, on the other hand, answers, if you leave the burner on forever, will the temp be high enough to cook your Hot Pocket like a big boy who's not afraid of the toaster and just likes it cooked like this? Of course, this is a massive oversimplification of the two subjects, but this is about continuum mechanics, not my fear of everything heat, which is ironic because I work in HVAC. On to fluid mechanics. First thing, fluid does not mean liquids. It means liquids and gases. So, drinking out of the garden hose as a child, that's a fluid mechanics problem. Doing whippets at 2 a.m. at your buddy's house when you were 16, also fluid mechanics. In less stupid terms, fluid mechanics is the math of fluids either in motion or not in motion. The distinction between solid and fluid is that a solid can resist shear stress by a static deflection. A fluid cannot, as put by the legendary Frank M. White, who has two excellent books on heat transfer and fluid mechanics called, well, Heat Transfer and Fluid Mechanics. I never said he was legendary for coming up with interesting titles. Fluid mechanics primarily deals with the flow of fluids and how the properties of the fluid in question affect the problem. A quick note is that simulations are generally necessary to do complex calculations, so as an undergrad, simplified problems and geometries are to be expected, which leaves us with non-fluid mechanics, which is a stupid way to say solid mechanics. My favorite of the three subsets of continuum mechanics is solid mechanics. Well, to be more specific, 2/3 of solid mechanics, because it is also broken down into three subsections, and I hate one of them. One of the good ones is statics, the other is mechanics of materials, and the bane of my sophomore year, the third, is dynamics. I plan on going into greater detail on these in different videos, but there's no harm in quickly going over them. Statics, as implied by the name, is the reactionary forces and moments of things that do not move. Mechanics of materials is the reaction of materials under applied forces. Mechanics of materials generally uses short periods of time, but for longer periods there is a concept called creep. Quick example of the difference between statics and mechanics of materials. Think of this. Someone is standing on the edge of a diving board. They are applying a force at the end of it because gravity exists. And the person weighs X pounds, or kilograms, or slugs, or whatever you people use. So, how far down is the tip of the diving board from where it rests without someone on it? Now, is that a statics or a mechanics of materials problem? Well, it's both. It's a trick question. Mechanics of materials technically does not solve for any forces or moments, and statics does not allow any movement, including bending. So you must first solve for the reactionary forces before you can move on to how far down it is bent. How I like to think of the difference between statics and mechanics of materials is like that of a function. Your statics problem is invariable, and the mechanics of materials problem is variable. Or, more simply, the material is variable. Meaning, you can change out a material without any change to your statics problem, but things like how much the structure bends, or if it breaks. I'm not delaying dynamics. This is a really good example. I should honestly just keep going on with this. It's very important. Dive board mechanics is an emerging field. Dynamics is honestly dying out. When's the last time we tried to go to the moon anyways? I'll go over dynamics when we try to go to the moon again. Okay, fine. Dynamics. Dynamics is things that move. You throw the ball and it drops because Newton was assaulted by an apple. And those vinyl records hipsters listen to spin faster. The closer to the center the needle is. Done. Well, hopefully you now have a shallow introduction to continuum mechanics and the basics of the subjects inside the umbrella term.